Okay, I really appreciate everyone who showed up today for the class. This is a good number to see, actually. I was willing to send a message or announcement saying that it would be an online class today or Zoom section thing, because you already have the link. But we've talked about that here in the department, and they said as long as classes are not canceled, so there's no need to send that announcement. So it could be okay if people showed up. And I was already here, so I thought it would be great to see you around because I'll be doing the class online anyhow. But I appreciate your attendance. I'll be definitely taking that today. Uh, so I think this. I see today actually large participation also on Zoom. 25 participants so far. We still have around 25 here, maybe. So this is really exciting to see people are coming in to the class. Even I expected to see less than that. So who could remind us what we were doing last time before we stopped? Transformers. We moved now. What? Period system. Now we'll utilize actually both of them in the coming sections. And we'll be doing something ahead of that related to the phase shift. Okay? The phase shifting issue. Can someone remind me why do we have that problem in the transformers? From one side, okay, y to delta. What about like y to y or delta to delta? We don't have that issue? No, we don't have it. There's no phase shifting if we are having the primary side as y and the secondary side as y. So we don't have that problem. It could be easier. But there's something interesting that seeing that phase shift is very often because of the load nature. Can someone remind me about the benefit of the Y connection? Is there any benefit of that? Yeah. Yeah, great. Actually, this is the main thing about the Y connection is that we have that neutral connectivity, which help us get rid of any excessive current in the circuit in case of certain unbalance. But how much would be the current in case everything was balanced, there was no problem in the circuit? How much would be that IN? What? Yeah, I did not hear the person who said that before. So in the regular case, it would be zero because there will be no excessive current flowing, so IN will be useless. But it's very important in case we had a fault, we should have certain path for that extra current to get out of the circuit. What about a good thing for the delta connected circuits? Is there any benefit of having a delta or just a regular shape or form? Yeah, could be. Actually, it's more computationally intensive to have a delta. But if you have a delta as the primary, it would be easy to have a delta on the secondary. Yeah, it could make it easy. But there's something very nice about the delta. Uh, I think like mentioned that maybe briefly before. It's the ability to keep the harmonics or the nonlinearities or the bad things within the delta. Since you don't have that neutral connection, sometimes actually a third harmonic, which is harmful, uh, may not be considered as a fault. Okay, it's some nonlinearity in the system. So it's not a fault case, but it's not good to have on the system Because let's say our regular systems are either 50 or 60 hertz, but having higher than that frequency could cause problems to our devices. So the delta connected equipment have the ability to restrict or to confine that nonlinearity or the third harmonic within the delta. It will not be getting out of that. So mainly in connections related to generators, let's say, they have that delta connection to make sure all those bad things will remain restricted. Um, so I think this is some introduction about the coming things. I think I went through this circuit here. So we had three-phase transformer, 3 units attached to each other. Can someone remind me about the connection here? Why? Okay, I think you can see that here. And we see neutral connections. We could see a YY connection without the neutrals, but this is a good one. And we went through the typical ABC positive sequence, and we figured out on the secondary side, we'll have an equivalent also ABC connection with no phase shift. Okay? Is that clear to everyone? Because there's no difference in the two sides, so it came out to be exactly almost the same. The main difference, here's the input, here's the output. So for the negative connection, it'll be also the same, but we reverse the order of the phases. So instead of having A, B, C, we will have A, C, B. Okay, can you see the difference? Having the negative connections or polarity is not too important to us, but it's something good to know. Okay, because sometimes you might see the polarity is reversed or so. It's not a mistake actually. It's just another sequence. So here in this circuit, I think we need to do the modification. Yeah. The only thing that we have new here is that instead of a YY connection, the primary side is still the same. No change from the previous figure. On the secondary side, we see that we have a new connection now. I think I've tried to do that here on this drawing. So I put the three phases with their windings, and the main change there is that the connectivity between the phases now it looks like in series. You see this connection? Okay. Can you see the difference between those two sides, this one and that one? Do they look different or not? This is important to see because sometimes you'll be given figures, but they don't mention their connectivity. You need to figure out whether Y or delta connection. So there's no simpler way to understand that other than following the lines. So let me go to step 4, where they have written step 4. You'll see a winding starting from A, small a, which means this is the secondary phase. It goes into the first transformer. We see that dot, which means that X1 and H1 are in phase, okay? And then we see a winding coming out from there. It goes down to X2. Then we establish the delta connection, okay? Because they are directly related. From X2, it goes to X3. Can you see that? I'm asking those questions because usually people look at the figure and they don't know what's going on. I'm trying to make it clear that this is the difference between the two connections. And then from X3, I see the winding around the third transformer, and then where it goes. Can you let me know? It goes, yeah, again to X1. So we made the loop. It seems that we connected 3 items like that, and then we came back here. Although this does not look nice, but if I want to make a transformation for this, it will be equivalent to let me make this shape nicer. If I want to take here a few connections for measurement, let me take 2 points and flip this figure. So I'll have 2 points here with delta, and then another one here and another one here. Okay? You can modify the shape of the lines. We don't care. This is all a line. If I make it like that instead of this thing, it's still the same line, you know? Then we see here three, other than that loop, I can see a connection for A, a connection for B, a connection for C. Those are at those points. Okay? Those outer connections are A, B, C. So I think now the connectivity is clear to everyone. Okay? Let's talk about the angles here. So we expect a phase shift. So let's prove that or show the difference. If I ask you to trace the phasors on the primary side, what would you do? You initially have them. Those are given. If I tell you it's in the positive sequence, so you already know that you have a neutral, and then you have A, you have B, and you have C. And those are in positive sequence. I'm referring to this to be the positive direction. Okay? My interest now is to know the connectivity or the equivalent representation of the connectivity on the secondary side. Okay? So if you read the book, they'll take you up and take you down, take you left, take you to the right. This is what typically they are writing. Go left, go right, go down, go up. I think you'll be lost here, mainly in step 4, when it's the time to calculate the angle or figure out the angle. They just tell you phase A is connected to dotted terminal H1 appears to the right, and that one appears to the left, and X2 must be down. We're not doing that. Okay? We could do it actually in a smart way, in an easy approach, which I've learned from my previous professor. This is your origin. I think I should zoom out. Okay. This is what we already had. Is that right? Step 1 is just to take each branch of that to the associated transformer. So AN, I just move it to the first transformer because that first transformer is related to A. Okay? AN is moved into A. This is step 1. And then BN is moved in the same inclination to B because it's the phase connected to B. And you have CN, you should move it in the same inclination also to C, to face C. You have no other choices. You will not take AN to C, for example. It's not related. So in this method, you have divided the 3 phasors among the 3 transformers, each one with the one associated with. Okay? Now, about labeling, we don't care. You keep the same labeling. So if AN here was like that, when you move it up to the transformer, it will be in the same naming. You don't change anything. So the primary side is easy. We just divided the 3 phases and put each phase where it should be. Okay? The thing that we need to know is about the secondary side, how those 3 phases would look like. So on the primary side, they were like that. Okay? So I need to know how they would look like here in the secondary side. The first step is to trace them as they used to be on the primary. So you don't change the orientation of each line, okay? The second step is to make the proper naming for each side, okay? For each line. For AN, A is determined. So you put A as a small letter because this is secondary, and we leave the N for now because there's no N in the delta connection, okay? For BN, we do the same. It's in the base, so I keep B there. Don't put it up. You'll be reversing the polarity. For CN, you do the same. You put small c here. N is no longer existing. That big N, there's no connection for it here. There's something else we need to figure out. So, how would I determine what's on the other side? It's either B or C. So, how should I know on this one? I need someone to help me now. So, what should be the connection here? Yeah, I think we can see that it's B, but I'll prove it in some other way now. What about this thing here? C or A? C. What about the third one? A. Well, I think you could see the result here. So I'm asking you, and we are just reading now. It's not a test, you know? We're just reading. But how could I determine them in a good way is that A is given. I need to know this. Let's expect that we don't know that much. We are just following the figure. So if you look here at the figure for phase A, you have a connection for the winding at A and a connection to B. You see the winding? The windings, X1 is going to A, and from the other side, it's going to B. There could not be a C there. This is how we figured out that this should be a B. For X2, can someone do the same thing? What's getting into X2? B. And what's coming out of that? Yeah. And for the phase C, it's C and A. Is that true? If we follow the winding for C, let's say, we see that C is going into X3, and from there it goes up to A. Is that true? So that's how we determine the other polarities here and there. So finally, we just need to connect them all together. You get CA here with same orientation. Where's BC? This is BC. I get it down. And I get this first element, BA. They should close the triangle. If your orientation is wrong, it could come out like that or some weird shape, you know? So you could figure out, I messed up with the names. Now, this triangle has a centroid. Okay, this is a physical element in any triangle. It's like the midpoint of that triangle. Okay. To relate that to the phasors, the output phasors for us, we have like three connections from C to N, from A to N, from B to N, or N to B, whatever. So if I'd like to determine VAN, I should measure this thing here. Okay? What's needed to determine a phasor? Angle and what? Magnitude. Excellent. So I think everyone is aware of the topics now. So this would be the length of this vector, it will be the magnitude. Okay? And the angle, you just get your measuring device. Now you could use your phone, actually. I figured that out. And you measure this angle from the horizontal line. Okay? Because this is effectively the angle which is being measured here. It's either this one or that one. Those are equivalent. So you you could measure that angle, it will come out to be minus 30, okay? And this is expected because we know that there's a 30 angle phase shift from between y and delta or delta and y, okay? So this is how typically we use graphing methods to determine the angle difference or the phase shift. So this was just a proof of this triangle. And here they'll tell you now the same thing of what we did, but they have much more words and directions up, down, left, right. So people, if they are reading this, they might really get lost sometimes because they don't know what they are referring to. So we figured out that VAN at the primary leads VAN by 30 degrees in accordance with the American standard. So let's now do some example regarding that. Okay. Phase shift of Y to delta transformers. Assume that balanced negative sequences are applied to the high voltage winding of Y delta transformer shown in the figure. Determine the negative phase shift of this transformer. Well, they made one adjustment for us is that instead of positive sequence, we have now a negative sequence. And we'd like to repeat the same process to determine the angle. Okay? So my expectation is that it should be a 30 degrees angle, but the polarity might change a little bit. Okay? So let's see what's happening. They are repeating the same process now with only one exception. If we look to this figure, we'll see now we have A, N, B, and C. So what was the change now? Any change from before? Yeah, because we see now those were reversed. Is that right? Those were reversed. This is the only modification. So we do the same thing. We take those phasors up to the figure. We put AN there, BN, CN, and we put also the parallel lines from the other side, AN, BN, CN, but without naming them. So now I would have this is what we had now, and I need to determine the other, the secondary elements, okay? So how their shape would be. Should be like that. Those three. It's a negative sequence. Do you think I made the correct thing now? I shifted the lines. Is it okay for a negative sequence? So this horizontal one, it came to be like that shape, to be BM. Do you think it's the way? No? No or yes? Should we make some voting now? What about yes? Raise your hand if you think it's the right way. It should be like that. What about no? Well, we have a clear majority now. A clear majority. Well, I agree with them, with the majority, that this is the wrong way. We do not change the orientation of the lines. Effectively, we need to keep them as they were. So, because you reversed the polarity, but you did not change the orientation of the lines. So we will repeat them. We'll keep them as they are for the negative sequence. And I need some help with the naming now. What should I do? Let's start with ABC. A. Let me know where should I put A for the first line. Okay. What should I put on the other side? N? Oh, okay, let's leave that for later then. Or I think we can do it now. If you look at A, we have a connection to A and then to B. Can you see the B? On winding 1 here. This is the connection to A, and then it goes from here to B. This is the winding. So it's B. It's fine if you don't know it now. But we just need to confirm that. And let me put small a because it's the secondary side. So I need help from someone on the second one. So I put B up there. And then what I put down? C, let me check. Yeah, you're right. Is it clear now? Can you see the difference? And now the last one. A third volunteer is needed.
Let me C on the left and then A on the right.
Who's that?
That's me,
I
Justin
don't know.
Fausto.
Okay. So we put C, and then we have a connectivity to A on the other side. So now we grab those three created lines. So you put, let me take them as they are here, A, B, B, C, and CA. I just grab them all together and put them in the triangle. And this is the centroid now, N. And I'm interested in knowing the angle VN. Okay? This is VN. VAN. So let me make a horizontal line now and check this angle. How much alpha should be? 30? Yeah, this is right. Actually, this could be proven graphically. And this is a solid proof. If you make all those measurements and you measure the angle, it came out to be 30. This is a final proof. You prove that graphically, not by math. So we'll see just a difference. Instead of having an angle of minus 30, now it's 30, positive 30. So this is the main difference between positive and negative sequences. I think here you have the explanation why a delta Y connection is good. Okay? They are mentioning the things that having a delta connection is helpful in case you have third harmonics or any bad component. It could be confined within a delta. But having the Y connection is good for having its neutral connection to eliminate, let's say, if you are on the transmission line and you had some strike, you should have some path for that very high current. So it will go away through that. Okay? Here, there's an interesting thing about delta-delta connectivity. There's certain advantage that one phase could be removed while the remaining phases continue to operate, but with reduced potential. I think the KVA rating will be reduced to 58%. So it won't be an open circuit. It will be still operating. If I had this delta-delta connectivity, and I had some problem and I opened this phase, okay? It was open. The rest will be still working. The rest of the connections will be still working, but at a reduced power, which will be like 58% of the original one. We'll prove that later in some problem, okay? This is very interesting about delta. And the Y, usually, if you miss a connection, you're done. So, I think now we'll start with something new. So, do you have any question? Okay, no questions. Great. So now we'll move forward with a reminder for the per unit equivalent. Who can remind me about that per unit, why it's needed or useful?
It simplifies the calculations because it kind of standardizes the values. Are you talking right now? The audio is
I
off.
think his audio's cut out.
What about now?
That's better.
Yeah, there was no connection actually. So we were saying that the good thing about the per unit equivalence of transformer is that we avoid the referral issue from primary to secondary. So there'll be one standard. We won't worry again about multiplying by a squared or dividing by a squared. So this is the huge benefit out of that. So here we could see some representation of a three-phase transformer from primary to secondary. We can see H1, H2, H3, X1, X2, X3. What's the difference between those two? What did we say about them? What's the H and what's the X?
The H is the primary and the X is the secondary.
The H is the high. The X should be add, but they put it X for some reason. I don't know. That could be some standard. So it just refers to primary and secondary side, but here they refer to the primary as H, which is the high. And we have some neutral grounding with impedance N. I'd like to mention that in any circuit, this does not have a neutral connection, okay? But neutrals could be without certain impedance. It's not necessary to have an impedance in the grounding. Why do you think in some places they put here some impedance? Yeah, but there's one more important thing. More important thing. What?
Hurt me mentally.
No, no, definitely not.
Could it be to help protect from lightning strikes coming up through the ground?
Even a wire without resistance will do the same. Actually, it will be easier because all that big current will go much faster. What's the benefit of having a resistance, let's say? What would a resistance do in a circuit? Let's forget about this course. Impede current. Okay. So having that resistance here will try to impede the current. So in case you had 1,000-volt strike and you had the impedance here almost nothing, it's not zero, but 0 point something, the current that will be circulating, it will be to the power 10 to power 9. Okay? It'll be a huge current. Even with the grounding thing, it'll be huge. But if I put an impedance of just 1 here, I'll be still getting rid of that extra current, okay? 1 ohm only, okay? But the order of the current now is 10 to power 3, okay? So you reduce the moving current or the faulty current by 10 to power 9 by 10 to power 3 by like 1,000,000 times, okay? 1 million less. 1 over this number, okay? So the impact will be much less for having that resistance. Anyhow, that was just an observation, okay? Sometimes when I ask such questions, it's just to maybe open some thinking areas to let us understand why do we have those components, because typically they are not just put in there for no reason, because in some cases you would see grounding without an impedance. What about this per unit equivalent circuit for balanced three-phase operation? What's that? What do we call this transformer? What? It has a specific nice name, actually. I hope people are studying transformers, or they are still busy with the previous chapter. This is an ideal transformer. There's no loss, nothing, no R, no X. So if I apply 100 volt on the primary side, on the high side, I'll obtain 100 on the secondary side. Okay? No loss at all. You see the path, it's empty, nothing. So this is an ideal case of a transformer where you don't see any of those shunt. Let's say I have this line. This is how it looks like now. Okay? This is ideal. But in the real case, you will have those things here and resistance, and then you have those two shunt elements. Do people remind those? Everyone. Okay? Well, you have a refreshment soon because homework 2 is on the way. Maybe on Friday I'll post that.
You said
Okay?
that the shunt branch is for the core, right? And then the resistance and impedance on the line, that's the windings.
Yeah, this is the equivalent circuit for a single phase transformer with all those components. So if I apply EH here and EV here, it's impossible for them to be the same. Impossible. Okay? Because there'll be something going in here. So now I was just reminding everyone about this ideal transformer, okay? It's definitely fine not to remember it right now because we're not being tested or so. I have here some rules so that we could do this per unit representation for this transformer. A common S base is selected for both H and X terminals. The ratio of the voltage bases is selected to be equal to the ratio of the rated line-to-line voltages. This is not new information, actually. We are just using S all over the system, the same. And we take V base at one side, and if you'd like to determine V base on the other side, we need to take into consideration the ratio, okay? So let's say if in this graph here, if the ratings are 480, 120 for this transformer. And S base, I told you, it should be 30 kVA. Okay? So what would be the numbers that I need here? I'd like to determine V base 1 and V base 2. What would be S base is common for all the system, no change. Okay, let's agree on that. What about V base 1? How much? 4? 480. Yeah. What about V base 2? Yeah. Yeah, it's not 480. Some people might go to tomorrow and put in the homework, it's 480 and continue solving the problem. No, we need to consider the rates. Here the rate is 4. 80 is equal to 480 by 120, which is 4. Okay? Then here they are saying again, whenever we have three-phase currents balanced, the neutral currents will be 0. We are aware of that. So those are the connectivity summary. For a Y-to-Y connection with neutral groundings, we see the per unit equivalent circuit. This is the complete representation, figure A. Can you see that? For figure C, it's the same thing, but delta to delta connection. We still have that shunt branch there. Okay? Our main issue happens with Y delta or delta to Y connection. Okay? You can see that the transformation of J30 to 1 for that connection. This is what we were solving before. So this is just a reminder for you about the connectivity in the transformer. Let's do a question now, some example. Voltage calculations, balanced Y to Y, delta to Y connection, transformer. Three-phase, two-winding transformers, each rated 400 MVA. So I get S here to be 400. 13.8, 199.2 kV. This is the ratio. Of the primary to the secondary side with a leakage reactance of 0.1. What does 0.1 represent? I need some help here.
That the reactance?
Yeah, it's called reactance. Reactance of what?
The windings.
The core? It stands to be here for the equivalent transformer. I'd like to see the figure. Yeah. When I say equivalent reactance, it stands to be for the Wool transformer. So they made all the calculations for you, and they said this is the eventual value of the equivalent reactance of the system. So you have a source, VAN, and you have that load, VAN, you see capital, and then you see there's something within, which is the equivalent reactance of the system, which came out to be 0.1 J. So the question is that at first, on the source side, it's always Y connection. But for part A, the secondary side has a Y connection. For part B, the secondary side has a delta. You can see the difference on the figures. So, and this popped up here, the 30 angles, because of the delta connection. So actually, this is the element which should cause a change in the calculation. So let's see what would we do here. He's saying determine, oh, I missed something here. The high voltage windings are connected in Y, a three-phase load operating under balanced positive sequence conditions on the high voltage side absorbs 1,000 MVA at 0.9 power factor lagging. I got some readings for the load. Okay? So he gave me here S gamma for the load. Okay? Those are needed if I want to calculate currents or so. There's no other way. So you would have a voltage now. You got some complex power. You could get the angle from here. How can I get the angle? How I can get the angle from the power factor? I'll start calling people.
Cosine inverse.
Okay. So I was looking at you here. Actually, I started to recognize the names of some of you, but not all of you. So we do that thing. We will take, let's speak about the per unit and things like that. So he told us VAN of the load is 199. So he gave me V for the load. He gave me S for the load. I can get gamma for the load. calculating the current is possible now. Okay, what's the rule which unites those two? S is equal to what? Okay, we're done. Because you have S, you have V, you could calculate I star. So this is what he's doing, but he would like to solve that in per units. So we need to normalize everything, make sure it's within that one range, and then make our calculations. So let's say if I take here 13.8, my base on the primary, 199 will be my base on the secondary. Is that right? So if I take V base, I call it H because of their names, 13.8, V base X would be 199.2. But there's something. You need to make sure if it's the phase voltage or the line-to-line voltage. Both work, but if you are willing to use the line voltages as bases, you have to multiply by radical 3. And this is what we are doing here. So I multiply by radical 3 to make sure this is line to line, because it will make my calculations easier. So here you'll figure out mysteriously that V base high, it came out to be 345, but it was here 199. Actually, he multiplied by radical 3 directly. Okay, so I'd like to note that down. And then to calculate I just divide S by V. So I get the V and I divide by S, so I get 2.008 kiloamperes. So taking this VAN as 1 per unit would give me VAN is 1 to 0 per unit, and then the I value, which I've calculated from before using this one as VI star, will be this thing, 1,000. And then you divide by the voltage, okay? And this is the angle minus cosine of the angle. And then you divide by 2.008 because this is the normalization thing, the I base. So you're getting the value of I in the base values. Is it clear for the people? You need to follow up about those calculations. What values did he take? I'll go again on that question next time because we're not done yet. We still have part B. So we'll explain it again. Just review until here. Okay? Where's the attendance sheet? Okay, great. See you on Friday.
I won't be able to make it Friday because I have a track meet. Do you want me to send you an email?
You can send me that form.
Yep.
Did you get that form from your coach?
Yep.
If you send me that, I'll waive your attendance.
Okay.
Okay? All right.
No, actually, he has this first.
Okay.